Good morning, everyone. Today we are going to finalize the last section, electric currents from magnetic field. Last time we talked about the phenomenon of electromagnetic induction and the generators. We said that in order to have current in a wire that is not connected to any source of electricity, we must have around it a change in magnetic field. Okay, and this change of magnetic field can be achieved by the motion of magnet in and out of the loop, or maybe by the motion of the loop in and out of the magnetic field of the magnet. Okay, so the most important thing is to have relative motion. Okay, it is to have a change in the magnetic field in order to have current in the wire that is not connected to any source of electricity. Okay, and we said that the electricity in our homes is coming from generators such as large power plants, such as like hydroelectric power plant, coal power plant, solar power plant. Okay, so all of these power plants, they use the same concept. They use generators. They generate electricity. How? They generate electricity by using, for example, the steam coming from burning fuel. For example, this steam turns the turbine, and then this turbine is connected to a core. Okay, and a core which is wrapped by a coil, okay, of wire. So and this wire or wires wrapped around a core is placed inside a magnet. So when it turns, the magnetic field of the magnet, the field lines of this magnet change. Therefore, the magnetic field change. Therefore, the current is induced in this wire. The charges which were at rest, they move now. There is a force that pushed them, that caused them to move. So we get current, and we know that the current can light up a bulb, for example, can do everything, can turn on any machine we want. Okay, so, but this current, we said, it's called alternating current and not a direct current. Why? Because this current, it reverses direction every half rotation, every specific interval of time. Okay, because the current produced is produced because of the loop inside the magnet. Okay, so when this loop inside the magnet, when the wire here inside the magnet changes a position, also the current changes direction. Okay, so that's why we said it's called alternating current. It alternates direction. Okay, so we talked about all of these last time. Today we are going to talk about a new concept, electromagnetic waves. You all know it. Okay, it's not new actually, but here the formation of electromagnetic waves is new for you. Okay, pay attention with me. So according to Faraday, the scientist who discovered what? Who discovered that the current can be induced from what? From change in magnetic field. Okay, so according to Faraday, current, or we can say instead of current, we can say the word electric field. Okay, you know, girls, current is moving charges. So whenever you have moving charges, you have around the charges what? Electric fields. Okay, so according to Faraday, current or electric fields are created in any region where a magnetic field is changing. So whenever we have a change in magnetic field, we have what? Current. Therefore, what do we have? Electric field. Okay, according to Maxwell are the one in section 2. Okay, in section 2, Ørsted, we learned that Ørsted or Maxwell, because both of them they found the concept, we learned that whenever we have change in electric field, what means change in electric field? Whenever we have a current passing in a wire, you remember when we have a current passing in a wire, we said we will have around this wire magnetic field, and it has the shape of concentric circles. This is from section 2. Okay, so according to Ørsted in section 2, we said whenever we have current, okay, we have magnetic field. So a magnetic field is created in any region of space where a current, or we can say instead of current what, an electric field, okay, because as I told you, current, moving charges, it means electric field. So a magnetic field is created in any region of space where an electric field is changing with time, okay. Current, it means moving charges, so around each charge we have electric field. These charges are moving, so the electric field is changing, okay. It's just another way to write the concept, okay. So how can you now relate these two statements together? So from section 3, according to Faraday, we learned that electric fields or current are created in any region where there is a change in magnetic field, okay. From section 2, we learned that magnetic field is created in any region where electric field is changing. So these two, electric field and magnetic field, they are what, closely related. Whenever you have magnetic field, okay, change in magnetic field, it will produce what, current, so it will produce electric field. Section 3, okay, whenever you have electric current or electric field, so this will cause what, you will have magnetic field. So these two, they are always like together, okay. So these laws are inverse of each other and lead to the concept of electromagnetic waves, okay. At the beginning of the year, we learned about electromagnetic waves, light, and all types of light, radio, micro, gamma, infra, all the types, okay. And we said they are called electromagnetic waves. Why they are called electromagnetic? See this word, it's made of like two words, electromagnetic. So it means that it's the combination of two fields, electric field and magnetic field, okay. So light or electromagnetic waves are produced from the both combination of magnetic field and electric field. Pay attention with me here. This figure shows an electromagnetic wave or light, okay. It's colored. The yellow one, the yellow wave, it represents the electric field, and the purple represents magnetic field. And as you can see, they are perpendicular. The black line is the light produced. So whenever I have these two together, electric field and magnetic field, I have light. Why? Because girls, whenever you have electric field, the change in this electric field will produce magnetic field, and whenever I have magnetic field, the change in magnetic field will produce electric field. So they are like feeding each other, okay. So once you have them, they will never like stop. So that's why the light can travel through vacuum, okay. So electromagnetic waves consist of electric field and magnetic field waves that are perpendicular to each other. So they are perpendicular to each other, electric field and magnetic field, and they are perpendicular to the direction of wave travel. Electromagnetic waves can travel through empty space because the changing of electromagnetic field regenerate each other, okay. So they are feeding each other, they are regenerating each other, electric field and magnetic field. So that's why the light can travel through empty space, okay. It doesn't rely on matter like such as sound, no, it relies only on these two, electric field and this region and magnetic field, okay. And also a note, you know girls, you remember from the first chapter you learned in this year about electromagnetic waves, we said that they are transverse waves. I told you like that only memorize it like this, you are going to understand it more at the end of the year. Why? Because now you can understand it. Transverse wave, it's any wave in which what the components are perpendicular, right? And here in electromagnetic wave, as you can see, we said that electric field and magnetic field are perpendicular to each other and they are perpendicular to the direction in which the wave is traveling. So that's why it's classified as transverse. That's why I told you at the beginning of the year, all types of electromagnetic waves, radio, micro, infrared, visible light, gamma rays, ultraviolet, x-rays, all of them are transverse waves, because in all of these types are made of electric field and magnetic field, and in all of these types the electric field and magnetic field are perpendicular to each other and perpendicular to the direction of travel of the wave or of the light. Okay, so this was everything about electromagnetic waves. The last concept in this lesson is about something called transformers. Okay, as now the name suggests, transformer, it means like it transforms something, right? What does it transform, do you think? It basically, girls, transforms the voltage from a value to another. Like you give some input voltage to a transformer, and this transformer will take this voltage and change it, transform it to either higher voltage or lower voltage. So we will talk about the working of this transformer and the description, the components of it. Transformer is a device composed of two unconnected coils. Okay, look at this picture here. This is a coil, okay, wire wrapped around this core. The rectangular block here, it's a core, okay, iron core. So we have wire here, it's wrapped around one side of this core, okay, making a first coil, and we have here another wire, okay, wrapped around the other side of this rectangular core. Okay, so this one, and this one, these coils, they are not connected to each other at all. Okay, so it's composed of two unconnected coils. Here you bring a wire and you wrap it around it, around one side, and another wire and we wrap it around the other side. Okay, so usually wrapped around a soft iron core that increase or decrease the voltage. Okay, so transformers, as we said, from its name, it transforms. What does it transform? It transforms the voltage. Okay, I will explain the use of transformer and why we wanted to transform the voltage later. Okay, so the most important thing now is to understand the here the components of a transformer. So it's made of three things: coil A, let's say, or coil 1, coil 2, and the iron core. Okay, this coil, girls, so where how we will connect it? We will keep it like this one and this one without any connection? For sure no. Let's see together. So the first coil we will it's called primary coil. We connect it to a source of electricity. See, this is an outlet, okay? We connect it to source of electricity. The second one, we connect it to the device or the appliance we want to turn it on. Okay, so what will happen now? The first coil is connected to source of electricity, and the second coil is connected to a lamp, for example. And these two coils, they are not connected to each other at all. Okay, how will the lamp light? How will the bulb here light? It's not connected to any source of electricity. Okay, so let's understand this together. This wire is connected to source of electricity. So what do I have in this primary coil? I have current, right? I have current, and it's alternating current. So current here is flowing through the primary coil at the beginning only, not the secondary. So how does this bulb light? Okay, according to what we learned, we said whenever we have current, section 2, whenever we have current, okay, moving, electric charges moving, this current will produce what? Magnetic field around the wire. So here I will have magnetic field, MF. Okay, it's represented by these green lines. Okay, so magnetic field here is produced. Okay, so this magnetic field here is produced around this whole core. Okay, this whole coil of wire and the core, iron core. And whenever I learned also from section 3 that whenever I have magnetic field, a change in magnetic field, okay, around a wire, the charges in this wire will move and current will be induced. Okay, so because of the magnetic field produced by this current, this magnetic field then produce current where? In the secondary coil, and the lamp turns on. So here we use the concepts of section 2 and section 3. Okay, so these coils, again, they are not connected to each other, but how the device works? It works because the current here is induced from the magnetic field, okay, produced by the first coil. So placing a core within the coils will intensify the magnetic field. What means intensify? It means like increase its intensity, or make it a stronger magnetic field. Okay, that's why we put a core, iron core. We don't keep that the coils without anything inside them. Okay, we put a core because we learned that whenever we have magnetic field around an iron, the iron will be magnetized, right? So this will increase the magnetic field. The magnetic field produced by this current add to the magnetic field produced by the iron to give a stronger. So that's why always when we want to increase the strength of a magnetic field, we use an iron core inside the coil of wire. Okay, so the secondary will intercept more of the field change here. So transformers, as we said earlier, it consists of 2 coils of wire wrapped around opposite sides of closed iron loop. The primary one, how to define the primary coil? It is the one connected to the current or to the source. Okay, the source here we said it's power outlet. Okay, see, it's outlet. Secondary coil, it's the one connected to the appliance such as what? A lamp. Okay, 2 coils of wire wound are on the same iron core, so that changes in the magnetic field of the first, which is the primary, induce what? The voltage in the second, or induce the current in the second, the same thing. The magnetic field building around the primary extends to the secondary. Okay, so this about the explanation I already said here. Now we have 2 types of transformers. We have step up transformer and we have another transformer called step down transformer. From their names, they are very easy. Listen, we will start with the step up transformer. What can you notice here? This is the primary coil, so it means it is the coil connected to what? To source of electricity. So here I have current. Okay, quickly. So this current, what does it do? It produces magnetic field around it. Okay, magnetic field. This magnetic field, because it's strong now, because this magnetic field will cause the iron also to be magnetized. So the iron is magnet now, and it has a magnetic field around it. So the magnetic field of the iron adds to the magnetic field produced by the wire to give a stronger magnetic field. So this magnetic field induces what? Current in the second coil. I'm just repeating the details I already said. Okay, so the current is induced in the secondary coil, and this the secondary coil is connected to the device we want. What can we notice now? Here we can notice that the number of turns or loops in the secondary coil are more than the number of turns in the primary coil. When you have like this, here it means that it is a step up transformer. Okay, what is the role of this transformer? This transformer is taking a specific voltage, let's say voltage equals to 10 volt, and it's making it 100 volt. So step up transformer, when the number of turns in the secondary coil is more than the number of turns in the primary coil, the transformer here, what does it do? It increases the voltage. Okay, so the voltage across the secondary coil is greater than the voltage across the primary coil. Okay, step down transformer is the opposite, when the number of coils in the secondary is less than the number of coils in the primary coil. In this case, okay, the role of this transformer is to decrease the voltage, meaning that the voltage across the secondary coil is less than the voltage across the primary coil. Okay, so we talked about what the voltage V. Okay, now I want to talk about something very important. You know, girls, that always when we give specific energy, this energy it will be used, all of it. Okay, so no new energy will be created. Okay, according to the law of conservation of energy, we know that energy cannot be created or destroyed. Okay, so the energy you give, the input energy you give, it should be the same as the output energy. And in real life, it will be a little more. The energy we give, it will be more a little bit than the output energy. Why, girls? Because always any device, even the transformer, some of the given or input energy will be lost as heat, okay, in the device. But if I want to talk about the perfect transformers, the ideal, that are not real, okay, but if I want to like disregard any loss of energy, I can say that the input energy, it's equal to the output energy, right? Okay, well, so, and we know that power from grade 7, it's energy per time. Okay, so if input energy is equal to output energy, meaning that input power input is equal to power output. Okay, the amount of energy given per second, it's equal to amount of energy given by the transformer per second. Okay, so the transformer is not going to create a new energy from nothing. Okay, and girls, if you remember the equation of power in electricity, what was it? It was current times voltage. If you turn back to the electricity chapter, so the input current and input voltage of the primary coil is equal to the output current and output voltage of the secondary coil, right? So focus please on this. Okay, and now I said that this type is what is step down. Okay, again, so input current times voltage is equal to output current times voltage. This input and this what? This output. So here we said this type is what? This type is step down, meaning that what? Now the voltage, the output voltage, the voltage given by that transformer is less than the voltage what given to the transformer. So this V is less than this V. Okay, I put 2 for example to make it easier for you. So here V2 is less than V1. Okay girls, but what? But this product, all of it is equal to this product, as I explained now. The power input is equal to the power output. How to make this possible? To make this possible, it means if this V2 is less than V1, okay, it means the current here in the secondary coil is what? Is more than the current in the primary coil. Okay, so the voltage now given by the secondary coil is less than the one of the primary coil, because the type of this transformer is a step down. So meaning that what? The current here is more than the current here. So current opposite of the voltage here. Okay, another example, step up. What means step up? It means this transformer is going to increase the voltage. So V2 is more or less? For sure what? More. V2 here more than V1. Okay, V2 more. Step up increases the voltage and what? Decreases the current. So I2 here is less than I1. Why? In order to make the products of these the same. Okay, power, the energy input, it's equal to the energy output. The secondary coil is not going to create any new energy or extra power. Okay, so here I want you only to understand that when we the step up transformer, when it increases the voltage, it means that it decreases the current. And step down transformer, when it increases the voltage, it means that it decreases the current. Okay, so energy is conserved, then the power output of the secondary coil is equal to the power input of the primary coil. We learned that power is equal to current times voltage. In a step-up transformer, the voltage increases across the secondary coil, but the current is reduced. Why? In order to maintain the same power. Okay, so this in case of what? Of perfect transformer. Ideal. What means ideal? Something like really perfect, that is not real. Okay, so here, because we are assuming that the output energy it's equal to the input energy, we assume that no energy loss, okay, in the transformer. So in real transformers, some of the energy you give to the transformer, some of the energy you put into the transformer, some of the input energy is always lost as heat. Okay, so in real life the output energy is a little what less than the input. Okay, but as I told you, we talk about the ideal case now. So as the power lost increases quickly when the current increases, why girls here? The power, so the power increase when the current increase. Here power lost, sorry, the power lost, okay, the energy lost. You know girls what, that when the high amount of electrons or moving charges move in the wire, These high amount of charges are going to make what collisions with the particles of the wire, okay, causing what? Causing heat. So always large current, we know that large current in electric circuit produce large heat, okay, and this heat can be easily dissipated, lost forever. So sending large alternating current through power transmission of over long distances result in the loss of electrical energy. Maybe you didn't understand it, but now you will. Pay attention here. Let's say that this is the power plant. What is the power plant? It is the one that generates electricity. Example, hydroelectric power plant that uses water, or coal power plant, the one that uses coal, or solar power plant, the one that uses the sunlight. Okay, but the result is the same. We need to generate electricity. Let's say we generated electricity, okay, so near this power plant they use step up transformers. Why? Step up, we know that they increase the voltage, okay. Why they use a step up transformer, girls? In order to increase the amount of energy? No, the energy is the same, it doesn't change. The energy always, the energy input equals to the energy output. But when I use a step up transformer, I increase the voltage and I what, as we said, decrease the current. Why I want here to decrease the current? Because, girls, this electricity or this voltage is transmitted over long distances from the power plant to the houses, to the offices. So this long distance, when I have, like, if I don't have low current, if I have high current, high amount of charges that are moving through these wires for long distances, what do you expect? These charges are going to heat up all the wires, so making what? Fire hazard, right? So that's why we need to decrease the amount of current passing through the wires. So we use step up transformer. Step up transformer, it increases the voltage and decreases the current. Okay, so always near power plant we use step up transformer. Okay, then again, before reaching the home or the office, do we keep it like this? No. Why? Because now I don't want this very high voltage, I want a lower voltage. In our home, what do we use? We use 120 volt, 230. Okay, so these voltages, in order to have them, okay, I need now to use a step down transformer. Okay, this maybe it's this figure clearer. Okay, so this is the power plant. The transformer used beside the power plant is step up. Why? Because I want to decrease the current, because this current or this electricity is sent for long distances, so I don't want to heat up the wires. We decrease the current, and here we increase what? The voltage. We increase it, girls, to almost like 120,000 volt. Okay, so this transmission, it occurs over long distances. Before home, before the consumer, we use a step down transformer. Step down transformer, it means what? We decrease the voltage and we increase what? The current. We decrease the voltage actually to an amount of 230 or 120, okay, in order to use it in our homes. This was everything. Here you have two videos at the end of the lesson. You can check them to understand better. Okay, so here I will read the last slide with you. To minimize such losses, electricity should be transmitted in form of low current. Always, in order to minimize the heating on wires, in order to minimize the loss of electricity, we want to minimize the current, and we use a step-up transformer. So power companies use high voltage and low current step-up transformer when transferring power over long distances. Step-up transformer is used near a power plant to increase voltage to about 120,000 voltage or volt. Step-down transformers are used near homes to reduce the voltage to 120 volt. This was everything. Thank you.